Okay, the recording has started. Great. Yep, you can.
All right, yeah. Then, yeah, thanks a lot for the invitation, Gianluigi. So, yeah, I'm Eric. I'm a PhD student at the University of Cambridge and also affiliated with the Max Planck Institute for Intelligent Systems in Tübingen, Germany. And yeah, I'm very glad to be here, and I'll be sharing some research that I've been doing with a lot of people over the past couple of months or the past year. And the overall topic will be on scalable Bayesian deep learning with modern Laplace approximations. So it's about, yeah, a particular type of algorithm called the Laplace approximation, which I will introduce, and yeah, some efforts to kind of scale it to deep neural networks and make it more practical. And yeah, if there's any questions, feel free to interrupt me at any time. I'm happy to take any questions. So first of all, I'd like to thank all my collaborators. So I'll be talking about 2 papers. Hopefully I'll have the time. And yeah, these are basically all the people I've worked with. There's Eric Lisnik from University of Amsterdam, which is, I guess, close to you guys. And then there's some people from Cambridge, James Ellingham, Javier Anturan, and my PhD supervisor, Miguel Hernandez Lobato. And there's a few people from Tübingen, Agustinus Christiari, Runa Eschenhagen, who are PhD students or master students, respectively, and Philip Hennig, who is a group leader in Tübingen. And then there's Alex Immer, a PhD student at ETH. And there's Matthias Bauer, who is a research scientist at DeepMind. And without these people, these projects wouldn't have been possible. So thanks a lot. So the overall motivation for this talk is that deep neural networks tend to make overconfident predictions. And I think some of you might be familiar with this problem. And it's kind of very critical to avoid this in especially safety critical applications, for example, healthcare or autonomous driving. We do not want deep neural nets to be overconfident, but we want them to be well calibrated and to kind of have uncertainty estimates to help them not make bad decisions. And one solution that has been around for some time and that's kind of somewhat principled is to quantify the uncertainty of the predictions of the model using Bayesian deep learning methods. And I guess your group, or at least some people in your group, are working on these methods as well. So I guess, yeah, I hope some of you are familiar, at least with like the high-level idea. And just as an example, in like a toy setting here, on the left-hand side, you can see some predictions of a neural net on some 4-class classification problem. And in blue is the confidence of the prediction. And confidence just meaning like the maximum softmax output of the model. And here we can see that basically everywhere, or almost everywhere, the confidence is very high at 1.0, which is kind of telling us that the model is maximum confident. And clearly this doesn't make sense, because if we go far away from these colored dots, the model should have low confidence, because if you're far away from the training data, the model shouldn't know what to predict, so the confidence should be low. But here we can see that it actually extrapolates very poorly and has high confidence far away from the data. And on the right-hand side, we see the same plot, but now with a Bayesian neural network. And here we can see that the Bayesian neural network is better calibrated in the sense that far away from the training data, it assigns very low confidence. So yeah, that's kind of the main idea. And then there's, doing Bayesian inference in neural networks is difficult. One particular approximation that people have been using since the 90s, I think, is the Laplace approximation. And it's actually a very simple idea. And the idea is as follows. We first obtain just a point estimate over the weights using map inference. So essentially we just do normal SGD training, if you will, which is visualized here. So we just try to find a local minimum of the loss. And then once we found the local minimum, we infer a Gaussian posterior located at this map estimate that we got with some covariance matrix. And here the covariance matrix is the inverse of the Hessian of the loss, basically capturing the curvature at the local minimum. And that's basically it. So you just estimate a Gaussian on top of the local minimum that you got using SGD. And this is a very simple idea and has been used already in the 90s. And back then, obviously, this was also easy to do because the models were very small. And yeah, the nice thing about this is that it's very easy to obtain this map estimate because in deep learning, we know very well how to train our models. So this is something we're very good at. The main issue here is that getting this Hessian, then we need to estimate the covariance matrix, right? To estimate the curvature is very difficult to do in modern models. Like back in the days, it was easy because the models were small, but nowadays it's getting more and more difficult because the Hessian scales quadratically in the number of weights of the model. So if your model has 1,000 weights, the Hessian is 1,000,000, which is still feasible. But if your model now has 1,000,000 weights, the Hessian is of size 1,000,000 times 1,000,000, which is getting infeasible very, very quickly. And so, yeah, this is kind of one of the reasons why I think recently people haven't used this method as much. So is this clear, this approach, or should I explain it a bit further? Otherwise, just interrupt me if it's not clear.
So basically, you train a model with maximum a posteriori, right? And then what's the following step with the Hessian?
And then you just fit a Gaussian distribution where the mean is kind of this map estimate. So the mean is this local optimum. And then for the Gaussian, you also need a covariance matrix, right? And the covariance matrix here is just the inverse of the Hessian. And the reason is because the Hessian kind of captures the curvature of the loss surface. And the Gaussian should ideally kind of fit also the curvature of the loss, right? If you assume you're in some kind of valley, then the Gaussian should kind of fit this valley somehow. That's kind of the idea. So it's a very local approximation, right? You just approximate this single node.
Okay, thanks.
Yeah. So that's kind of the approximation that people have been using or not using anymore. So yeah, these days people use like more variational inference methods, for example, as I think some people in your group also work on, and also more ad hoc methods, which are not even principled or not even motivated by Bayesian inference, for example, ensembles. And there's different reasons for this. I think one reason is that Laplace approximations are very old. So they have been proposed originally by Laplace in the 18th century, a while ago. And more recently, they have been applied to, this approximation has been applied to neural networks in the 90s by David McKay. Yeah, I guess we can't do anything. It's just an old method, probably. Maybe that's why people don't like it. Maybe it's too simple because it just approximates the posterior using a single Gaussian, right? So it's very local in a sense. And then you might think, well, it can't be that good if it's such a simple method. And we actually show that it can be quite competitive. Using recent advances to scale it, you can actually make it work quite well. And the third issue might be that it's very impractical because you have to compute this Hessian to estimate kind of the curvature for the covariance matrix. And yeah, there have been recent efforts to also make this more tractable and approximate the Hessian, for example. And we will talk about some of these ideas in this talk. And yeah, so the structure will be, I'll hope to talk about two papers. One is addressing the question of how to make this Laplace approximation more scalable and scale it to modern neural networks. And what we did in this paper was we propose a method where we perform inference not over all the millions or billions of weights, but we only perform inference over a small subset of the weights. And that should be more tractable because then the Hessian only scales quadratically in the subset of the weights that you choose. So if that subset is small enough, then the method is scalable. And this was a paper presented at ICML earlier this year, where I also met Gianluigi at the poster session, actually. And then the second paper asked the question of how we can actually make the Laplace approximation more practical and also easy to use for practitioners and for maybe researchers who want to apply it and try it out. And there we developed a simple library in PyTorch, which allows you to play around with the Laplace approximation and apply it very easily to a neural network. And this is a paper that was recently accepted to NeurIPS, and which we will present later this year. And yeah, depending on the time, I can talk about both. Maybe I won't be able to talk too much about the second one. Let's see. But I'll start with the first one. Are there any questions so far, or is like the high-level idea clear?
Yeah, okay.
All right. Thanks. Yeah, so this is, as I said, this paper with these collaborators asking the question, how can we make the Laplace approximation more scalable? And essentially, yeah, just to formalize the problem a bit, the goal is to infer a posterior distribution over the weights of a deep neural network. So if W are the weights, then we want to infer a distribution over W, not just a single point, but we want to get a full distribution. P of W given y and x. Y and x is just the training data, training inputs and training outputs, x and y. And as you probably know, there's like Bayes' theorem telling us that the posterior is proportional to the likelihood, which is simply the probability of the data given the model times the prior distribution over the weights, which you have to define somehow. And yeah, the issue is that modern neural networks are just too big. So even while computing it exactly is basically always intractable if you have nonlinear models. But even approximating this posterior distribution P of W given the data is very difficult in modern models. Because as you know, models are growing and growing, and the latest models can be up to 100 billion parameters, which is like way too big to do anything meaningful with it. And for this reason, often people make very simplistic assumptions on the posterior. For example, they assume that the weights are not correlated. They assume that the weights of the posterior are independent of each other. And this is one of the main assumptions that people often make. For example, if you do variational inference, this is called mean field, this assumption that you assume independence between weights. And this makes the problem tractable because now you don't have to worry about correlations anymore. And your Hessian essentially is just now a diagonal matrix, or the covariance matrix is just a diagonal matrix. But the issue is that some papers have shown that this makes the performance much worse. So you get very bad uncertainty estimates, and you don't actually improve the calibration of your model if you make this assumption. So we try to do something better than this. And the main observation that we make is that most of the methods that exist these days, what they try to do is they try to do Bayesian inference over all the weights of the neural network. And since there are so many of them, this is just a very difficult problem. And the main question we ask in this work, do we actually need to estimate this posterior distribution over all these millions or billions of weights? Or can we actually get away with estimating the posterior over only a very small subset of the weights? And this is basically the whole idea. So we observed that since neural networks are so heavily overparameterized, the accuracy of a deep neural network can actually be well preserved by a small subnetwork. This is an observation that has been around actually for a while. And this is explored in the area of neural network pruning. And there what people essentially do is they take a neural network, they train it, and then they kind of remove some of the weights after training often. And they have shown that if you do this, you can actually preserve the accuracy of the original model by just ignoring some weights which are not important. But of course, all these approaches, they only have focused on accuracy. And in our case, we don't really care about accuracy so much, but we care more about the uncertainty in the posterior. So the question that we asked ourselves is, can we also preserve the uncertainty of the model using a small subnetwork, not just the accuracy? And yeah, we found that yes, you can actually preserve the uncertainty quite well to some degree. And I'll show you in a second how we try to do this. Yes. And essentially the idea is, as I said, we propose a particular kind of approximation where we split the true posterior distribution on the left-hand side. We approximate it using an approximate distribution Q of W. And what we do is we split the weights W into two sets. One set is the subnetwork, WS, that we want to do inference over. And then the second set are just all the other weights, which are not in the subnetwork. And this is kind of two disjoint sets. And now we kind of split this posterior distribution into these two sets. And one is essentially a distribution over the subnetwork. So now we consider P of WS given the data. And we consider delta functions over all other weights. And delta function just means that there's no distribution over them, but we just keep them fixed at some fixed value. So we basically just keep them at some arbitrary value, basically. So we estimate a distribution over the subnetwork, and we just use a point estimate for all remaining weights. And Now, the posterior distribution over the subnetwork is still intractable in most cases due to nonlinearities of the neural network, and therefore we still have to approximate it even more. So we have to introduce another approximation QWS, which approximates the posterior over the subnetwork. So is this clear, like how we kind of try to do this approximation? Otherwise, let me know. And yeah, basically now there's a few questions that we have to ask. One is, how do we actually choose this Q of WS? And I already hinted at the solution, which is the Laplace approximation, which I'll talk about in 1 second. And the second question is, what do we do with all the other weights? What values do we choose for them? We also need to set them to some value, right? And the third question is, how do we actually select the subnetwork in the first place? And the last question is, how do we then make predictions with this weird posterior? And to address the first question, I already gave you the answer. We use the Laplace approximation, so this is just the same slide that we saw before. But now the main difference is that in the second step, so after doing the point estimation, we first select a subnetwork WS. So we select a small subset of the weights, and then the previous second step is now a third step where we only do inference over the subnetwork. So we don't do inference over everything, but only over the subset of the weights. And this actually solves the scalability issue, because now we only have to compute this Hessian over the subnetwork. And since that can be chosen to be very small, it now scales only quadratically in the small size of the subnetwork, and this makes it scalable even for very large neural networks. So this is kind of, the approach that we take. And then essentially, this whole subnetwork inference method works as follows. We have 4 different steps. The first step is we do point estimation. So we use SGD to just get a local optimum of the loss. In a second step, we select a small subset of the weights, as for example illustrated here. In the third step, we do Bayesian inference over only this subnetwork. And in the last step, we make predictions using actually all the weights in the model. So for making predictions, we use both the subnetwork weights and we integrate out the posterior basically. And for the other weights, we just keep them at the point estimate to make predictions. So this answers the first 2 questions. So as the approximating distribution, we use a Gaussian distribution computed by the Laplace approximation. And for all the other weights, we simply keep them at the map estimate, basically the weights after training the model. So it's essentially quite simple. Now the next question is, how do we actually choose the subnetwork WS? And this is also quite an important question. And the way we do this is we formalize the problem to actually minimize the discrepancy to the full network posterior. So essentially what we try to do is we try to minimize, in this case, the Wasserstein distance, which we chose as a distance measure between distributions between the full posterior over all the weights and the subnetwork posterior over the subset, right? We want those two to be as close as possible. And a bit more formally, we can write it as this. The full posterior is just P of W given the data, and the approximate posterior is Q of W. And then we can just plug in the expressions that we had previously. So for the full posterior, we now just take the Gaussian over all weights. So this is actually an approximation that we have to do, since the true full posterior is obviously intractable, and we don't, we cannot compute anything with the true posterior. We have to make this approximation that the true posterior is kind of a Gaussian over all the weights, computed also using a Laplace approximation. And now the approximate posterior is again this 2-component posterior, where we have a Gaussian over the subnetwork and delta functions over everything else. And basically now we try to minimize this discrepancy between these 2 distributions. And again, this is unfortunately intractable because the left-hand side, so the distribution over all the weights, again depends on this Hessian H over all weights. So we actually cannot compute this objective, unfortunately, and we have to introduce another approximation. And now the approximation we have to introduce is that the true posterior has a factorized covariance matrix. So we have to assume that in the true posterior, so for the left-hand side here, we have only diagonal entries in the Hessian. And this is a very strong assumption, admittedly. And actually, it's the assumption that we try to avoid in the beginning. In the beginning, I said, we do not want to make a diagonal approximation, right, where we assume independence. But actually here we have to make it because otherwise it's intractable. And now you might think, well, but then can it be any better than assuming independence between the weights in variational inference or something? And the main difference here is that we only have to assume this independence for selecting the subnetwork. After we have selected the subset of the weights, we again do full covariance inference. So we do estimate correlations between the weights after we've selected the subset of the weights. But in order to choose the subset of the weights, we do have to make this assumption. But it turns out that this actually works much better than assuming independence over the weights for inference directly. So this works better than doing diagonal inference, for example, which we'll show in a second. So essentially, yeah, the subnetwork selection criterion we use works as follows. We first estimate a factorized independent Gaussian posterior over all the weights, which is fairly easy to do. There's a few methods that can do this. And then once we have kind of these marginal variances for each weight, we can select the weights with the largest variances. So again, what we do is we take the neural network, we estimate a factorized or an independent Gaussian for each weight. And then we take the weights with the largest variance estimates. And yeah, we show in the paper kind of that we can prove that this is kind of the optimal thing to do under these assumptions. But we can also intuitively understand this because I think it makes sense to say that the weights with the largest variances, they contribute most to the uncertainty in the posterior. Because the larger the variance for a weight, the more it will probably contribute to the uncertainty in the predictions. That's kind of an intuitive explanation. And this is kind of how we do it in this work.
But there are quite complex downstream nonlinearities, right? So it's a very loose, because the interpretation of the variance will be scaled by those nonlinearities.
Exactly, yeah. So obviously this intuition is quite loose. I guess it's just maybe one way to interpret it, but I agree. I mean, due to nonlinearities and other issues, the uncertainty in the weights doesn't directly translate into uncertainty in predictions. So
yeah, also even linearities, because there is just a linear scaling that can change the whole.
Exactly. And this is why I also want to point out, or I want to be honest, that this is probably the main limitation of this work, is that the way we choose the subnetwork is kind of difficult to do, and therefore we have to use kind of this heuristic. Although there's some theoretical motivation, it's still, you can view it as a heuristic, I guess. And therefore in future work, one of the most important future directions would be to develop better approaches to select the subnetwork, maybe ones that have more theoretical backing. But in the experiments, we will show that even this simple kind of approach performs fairly well. But I agree, I mean, this is kind of the main issue, I think. And it's also the most difficult problem in this whole algorithm, how you select the subset. And this is just one of the answers that we used, or the main answer that we propose, which might not be the best one, obviously. Yeah, but thanks for the comment. I totally agree. Yeah, any other questions on this? Otherwise, I'll just continue. Yeah, so now we answer this question. So how do we select the subnetwork? We minimize the Wasserstein distance between the subnetwork posterior and the full posterior under the assumptions that I mentioned. So independence between the weights, and also assuming that the true posterior is Gaussian, which are very strong assumptions, to be honest. And now the final question is, how do we make predictions? I already actually briefly told you. Essentially what we do is we use all the weights. So for the subnetwork, we integrate out the weights because we have a posterior distribution that we can integrate over, right? And for the other weights, we can just keep them as they are at the map estimate. So essentially we can combine the predictive accuracy of the map estimate with the calibration of the Bayesian posterior over the subnetwork. So we get kind of also good accuracy, which is actually an issue often with variational inference. You often get bad accuracy because you have to train the model in a different way. But since we can use standard methods to train the model, we retain the accuracy of the neural net, which is quite a useful side effect.
I'm sorry, can you elaborate this point a bit more?
Yeah, sure. So essentially, since the Laplace approximation has these two steps, right? We first use SGD or ADAM or whatever to obtain just a point estimate.
Yeah.
And we know in deep neural networks that we can get very good point estimates with very high accuracy. And what we just do here is we just estimate a Gaussian on top of this point estimate.
Yeah.
Essentially, this allows us to keep the accuracy of this point estimate, but in addition to that, get better calibrated predictions and better uncertainty estimates. So we don't sacrifice any predictive power of the map estimate. And this is actually, one advantage of the Laplace approximation.
Yeah. Although it's, I mean, you could still get, I mean, is it an advantage of the Laplace approximation? Because you can still have a variational inference loss, but only train the covariant structure with variational inference.
Okay.
Which could be that, I don't know if it's the case, but it could give you better coverage than the Laplace approximation. So it's more, I think it's more an advantage of optimizing the mode independently from the covariant structure, not much of the approximation scheme.
Yeah, I totally agree. That's a very good point. And I really like the idea of doing VI in the same way, where you fix the mode and just optimize the covariance. I think that would be an interesting idea. I don't know if anybody has tried that, but I think that would be interesting to compare to that. And yeah, exactly. So this can also be used with VI, I guess, in principle. But the Laplace approximation makes this more natural, because there it just falls out of the equation basically. For VI, yeah, you could also fix the mean, I guess. And yeah, and now I'll show you some experiments. So for 1D regression, it's a very simple toy setting. We use a small 2-layer fully connected neural networks with 2,600 weights. So it's very small. And yeah, we have this data set where we essentially have two separated clusters of data, if you look closely. So we have kind of one cluster of data points on the left-hand side and one cluster on the right-hand side. And in the middle, we don't have any data. And yeah, this makes it a bit difficult for inference, because we need to kind of capture high uncertainty in the middle. And if we just do map inference, so we just train a neural network without any uncertainty, we get this fit. So the fit is quite good. Now what we can actually do here, yeah, we test in between uncertainties. So we try to get good uncertainties in between these two clusters of data, which is kind of important, because far away from the training data, you want high uncertainties, right? So what we can actually do in this particular model is we can actually estimate a full covariance Gaussian, because it's a very small model, so we can compute the full covariance matrix. And if we do this, we get this very nice uncertainty structure where we have high uncertainty both at the boundaries and in the middle between the data clusters. So this works quite well. But obviously in practice, we cannot afford a full covariance Gaussian. So what people often do is they often do a diagonal approximation. As I said in the beginning, often people just assume independence between weights. And if you do this in this particular model, you get quite poor uncertainties. If you look at the middle, the uncertainty now has shrunken down to the same uncertainty as the map estimate. So basically there's no uncertainty left in the middle, which is quite bad. Now what if you use our approach instead? So if we use the subnetwork inference approach that we described, and we do, for example, inference over 50% of the weights instead of 100%, so we do inference over 1,300 weights, then we still get very good uncertainties in between the data and also at the boundaries. Now 50% is still quite a bit, so we can go even further down to 3%. So now we only do inference over 78 of the weights, and we still get actually quite decent uncertainties. And if we push this to the extreme, we only do inference over 1%, so only 26 weights. We actually still get much better uncertainty as, for example, the diagonal approximation. So this shows that by doing inference over only a very small subset of the weights and capturing correlations between a small set of the weights, we can actually do much better than, for example, a diagonal approximation over all 2,600 weights. So this is, I guess, one interesting finding. And now, obviously, yeah, this is just a toy setting. It's very simple. So you might be wondering, how does it scale to actually large-scale problems? Because in the beginning, I promised you this allows us to scale these methods to state-of-the-art models. And so in the second experiment that I'm going to show you, we consider image classification under distribution shift. So what happens if you train on some data set and you test on kind of a shifted data set? and we consider kind of a fairly large model, a ResNet 18. It's admittedly not state-of-the-art anymore, but it's, in terms of Bayesian methods, quite large, I think, 11 million weights. And what we do is we use this Wasserstein method to select a small subset of only 40,000 weights, which is just 0.4% of the weights, and do inference over only this small subset of the weights. And as baselines, we compare to a few popular approaches. We compare to the map estimate. So what if you just train the model and do nothing else? Then we compare again to the diagonal Laplace approximation. We compare to Monte Carlo dropout, which is a popular baseline that people often use, which I think is not state-of-the-art, but it's useful to see. Then we compare to deep ensembles, which actually is state-of-the-art. So there have been many papers showing that deep ensembles give you the best performance in many benchmarks. And another somewhat state-of-the-art method is called SWAG, stochastic weight averaging Gaussian, which is actually somewhat related to Laplace in that you also estimate one Gaussian, but it's still a bit different. But it's interesting. Yeah, if you're interested in this method and you're not aware how it works, feel free to look up the paper. And we tested it on different data sets. Here I'm only going to show you results on rotated MNIST, where you train on MNIST digits using the standard MNIST training set, and then you test on rotated digits. So you just rotate the digits and look at the predictions of the model. And here what we kind of plot is we plot on the x-axis the degree of rotation from 0 to 180. So we flip it upside down. And on the y-axis, we plot log likelihoods. And log likelihood essentially is a measure of both accuracy and calibration in a sense. So it tells you how kind of close the predictions are to the true ground truth labels, I guess. And also, considering overconfidence. So it penalizes you for being too confident in a wrong prediction, for example. And here, if we plot these different methods, we show that, we see that map, like all these baselines, they all perform the same essentially. So you see that map, diagonal Laplace dropout, ensembles, and SWAG, they all kind of get worse. So here, like higher is better. And as you see, if you rotate the digits more and more, the performance gets worse and worse. Compared to our method, actually, our method in dark blue here, it can retain performance much better than the other methods, and it doesn't drop as significantly. So essentially, the takeaway from this is that subnetwork inference is more robust to distribution shift than these other baselines. And these are just the experiments that I can show you now due to time constraints. If you're interested in more experiments, feel free to have a look at the paper.
Maybe does it hold to more complex data sets? Because this is still...
Yeah, so we also tried CIFAR10. There's a corrupted version of CIFAR10 where you train on CIFAR10 and you then corrupt the images. This is admittedly the most complex one we tried. So it's not yet scalable to things like ImageNet. And we are working to make it also scalable to ImageNet. So right now, there's limitations in both the model size actually and also the size of the output dimension. So in this case, if you have 10 outputs, it scales, but in ImageNet you have 1,000 outputs, right? And then you have other scalability issues, which we also mentioned in the paper and which we still need to address in future work. So it's obviously not the solution to everything. It's just one approach to make it more scalable in some way.
So, but does this big difference, is this big difference preserved in CIFAR?
In CIFAR, it's still noticeable. It's still very significant. It's maybe a little bit less significant than here. But yeah, if you look at the paper, it's still noticeable better.
And how do you explain it? Because it's such a big improvement. And I mean, intuitively, it sounds that it's still a kind of an ensemble method, right? So it sounds that should look that different from a deep ensemble. But it's a huge difference. So how do you explain it?
So I think one issue with the deep ensemble is that it's still, I think, overconfident. So it's still too confident. And with the Laplace approximation, I think you can make it, there's essentially a hyperparameter that you have to tune. It's the precision of the prior, so the variance of the prior, which pops up in the posterior again. This is a hyperparameter that you have to tune. And if you tune it properly, then you can get this good performance. If you choose the prior variance to be poor, then you also get worse performance. So you have to do some hyperparameter tuning. But to be fair, we did hyperparameter tuning also for the other methods. And essentially, I think for the Laplace approximation, you get higher gains. by tuning this parameter. And essentially, this parameter just controls the confidence of the model. So there you can actually trade off between under and overconfidence. So
the point is that you don't have this explicit parameter for the deep ensembles. You have got this implicit inference, and then it becomes quite more difficult to tune, which makes a lot of sense.
Exactly. Yeah.
Yeah, because there is all this debate, right? How Bayesian is the deep ensemble, and a lot of people say that they are, and I guess they're right. But now your point can be, yes, okay, but being implicitly Bayesian make your life difficult when you want to calibrate the prior.
Exactly. Yeah. So for ensembles, I guess you can also change the prior, right? Because the prior comes up in the optimization. Basically, if you use L2 regularization, you can choose the strength of the regularizer, which is, I guess, corresponding to the prior. But even if you tune that, the performance doesn't change much for the ensemble. So you're totally right, I think.
Yeah, but I think for the example, the connection is much more loose. So eventually you get quite decent Bayesian results in compared with Monte Carlo, but it's much more loose the way you understand the prior. So it's quite difficult. It doesn't surprise me that it's difficult to calibrate the prior in a deep ensemble.
Exactly. Yeah. So that's also what we observed. Yeah.
I mean, this is a small experiment. It needs to be seen on more scale.
Yeah, I have a very stupid question. Sorry for my cat is making me crazy. Because I mean, so imagine we want to compute the full covariance here of the uncertainty of the predictions, and we are using MNIST. For me, and this is the stupid question, how you know this uncertainty regarding numbers like, for instance, 6 or 9 that actually are I mean, who decide what is the correct prediction? So I rotated the 6s and 9. Yeah. So which number it is?
Yeah, that's a very good question, actually. And if you, there's some digits that are kind of rotationally, how do you call that? I guess, where you can kind of confuse them as for 6 or 9, or I think it's also the same for 1. Often you draw 1 is just a line, right? And then if you rotate, and there actually you have issues, because if you just plot the results for 6 and 9 or for 1, then the models will be quite bad typically, because they will be overconfident, right? Because as you said, if you rotate the 6, and you cannot expect the model to still predict a 6 because it is a 9, and even a human would be very confident that it's a 9 now, right? So in that sense, this kind of a limitation of this benchmark. And that's why here we have to average over all the digits. But if you just pick the digits where this doesn't work, then you get very bad performance for all the methods, simply because it's not solvable, right? Even for a human wouldn't be able to solve the problem there. So I agree. So that's one limitation of this benchmark, I guess.
I mean, I assume that then if you start from one, so if you have sequential input, then you can work on that somehow with uncertainty.
Yeah. If you observe the rotation sequentially, for example, then you could probably kind of learn that it's the same digit, just rotated. But if you just get presented a 6 and the rotated 6 upside down, you wouldn't be able to tell if it's a 6 or a 9, right? There's no way. So yeah, that's a very good point. So if there's no more questions on this, I would probably conclude for this part of the talk. So essentially what we did is we proposed a Bayesian deep learning method where we do expressive inference, so we capture correlations over just a very small subnetwork within the neural network. And we show that this can perform better than doing crude inference, for example, assuming weight independence over all the weights. And yeah, there's also a blog post, for example, if you want to know more. Also, obviously, the paper you can read. This kind of concludes the first part of my talk. And yeah, feel free to ask any questions now. Otherwise, I would briefly talk also about the second paper, although I'm aware that there's not too much time left. Yeah. All right. Then let me just briefly go over the second paper, maybe. There's also not much as much to say anyways, because it's not technical, the second paper. So in the second work, we now asked ourselves, okay, now if a practitioner, if you, for example, want to use the Laplace approximation, how would you do it? And then we noticed, well, it's actually not so easy to implement it, because you need to compute these Hessians and stuff. So we kind of came up with the idea of actually developing a library that makes it very easy to make a Bayesian neural network out of your model. And I'll show you how this is done. And this is kind of collaboration with these amazing people here. And yeah, as I said, this is a paper that will be presented in Europe's later in December. And so first of all, I'll show you kind of a quick kind of overview of the Laplace approximation and what you can actually do. So what are the degrees of freedom that you have when applying this method? So you start with a deterministic model, f theta. So it's just a neural network that's deterministic. And you can either train it, or you can actually also leave it untrained and train it later, which I'll show you in a second. But yeah, you just need kind of some model. Then the first thing that you have to decide, which weights do I want to treat probabilistically? So you can either do inference over all the weights, we can do inference over a subnetwork, which is the method that I just described, or we can also just choose the last layer, for example, which is actually a popular heuristic that people sometimes use. So people often just do inference over the last layer because it's very easy to do. So that's the first decision you have to make. What are the weights you want to treat probabilistically? Then the second degree of freedom you have, how do you want to approximate the Hessian? So typically, often people do use the full Hessian, but in some cases, for example, if you use all the weights, this is intractable. So you can also try to approximate the Hessian, and there has different approximations. One is, for example, a Kronecker factorization, where you assume kind of block independence between the different layers. Or you can just do a diagonal approximation, which is very simple. You can also do something like a low rank. So there's different ways to approximate the Hessian. And this can be combined with a subset of weights. So you can do all weights and a full Hessian. You can do a subnetwork combined with Kronecker factorization. You could do last layer combined with diagonal. So these are kind of independent things to do. And now the third question is, how do I tune these hyperparameters? So as I told you, there's this one hyperparameter that's very critical, which is the prior variance. And there's different ways to tune it. One way, if you start with a model that has already been trained, so if your model is pre-trained, which these days is quite popular, you can just download often a pre-trained model on ImageNet from the internet, right? So if you have that, then you can actually tune this prior precision post hoc after training. Or if you have an untrained model, what you can do is you can actually train and optimize hyperparameters jointly online, which was proposed in another paper recently. And this is quite cool because, yeah, it allows you to train kind of hyperparameters during training. And these are the two options that are supported also in this library. And yeah, after you did this, after you did training and hyperparameter tuning, you can then make predictions. And there's kind of different ways to make predictions. If you have regression, you can compute the exact predictive in some cases if you have a linear model, I guess. Or you have to do Monte Carlo approximation, which is more common. In classification, you have to do Monte Carlo because the closed form is intractable. Or there's some closed form approximations. Actually, there's an approximation called the probit approximation and one called the Laplace bridge, which are separate papers that people have come up with. But essentially, yeah, there's different ways to approximate this predictive distribution over outputs. So this is kind of the flow chart. So if you want to apply Laplace, you have to ask you all these questions, and then you can implement it. And yeah, fortunately, you don't have to implement it yourself anymore because we open source this library called Laplace, or Laplace Torch actually, because it's for PyTorch right now. We want to extend it maybe to other frameworks as well, but I think PyTorch is quite widely used, so we focus on that. And feel free to check it out on GitHub and try it out. There's documentation and everything. And yeah, the goal is essentially to dispel the myth that I mentioned, that the Laplace approximation doesn't work well, or that it's difficult to use or scale. So with this library, there shouldn't be an excuse anymore to not try to use it. And yeah, the goal is to give practitioners and also researchers an easy tool to give you uncertainty estimates, or also, yeah, get you other benefits of Bayesian inference. And yeah, for researchers, this is, for example, a very nice baseline that you can use to compare against. You can also use, for example, BNNs in a pipeline for something else. If you're interested in decision making or RL, for example, you can use a Bayesian neural network, for example, as part of the pipeline. Or if you develop new Hessian approximations, some people do that, then you can also use this as a test bed for the Hessian approximation, right? And just a short code snippet on how to use it. You can simply import a wrapper class called Laplace. Then you can first load the model, for example, a pre-trained model, and then you can simply wrap the model into this Laplace wrapper. And then you can just call fit, which computes the covariance matrix. And then you can optionally also optimize the prior precision, this hyperparameter that's important. And then, yeah, the library does everything for you, and then you can predict using in the same way as you would predict with a normal model. Just put in the test data and you get the predictions. Yeah. So it's very easy to use. And yeah, it supports all the degrees of freedom that I just showed you in the flowchart before. So you can choose the subset of the weights that you can consider. You can use all or last layer. Actually, the subnetwork approach that I described in the first part is not yet supported, but it will be supported in a future release. So stay tuned if you want to try out that method. Then you can try different Hessian approximations. It supports full Hessian, Kronecker factorization, diagonal, also low rank in the new release if you want to try low rank. Then it supports hyperparameter tuning, either online or post hoc, as I told you. And it implements various ways to approximate the predictive distribution. Yeah, more details in the paper. I don't think I have the time to explain these, but there's just different ways to approximate the predictive. And yeah, maybe a few words how it works under the hood. So actually, the most difficult thing for Laplace to implement it is these Hessian computations, right? You have to compute the Hessian matrices or approximate them. And that's the most difficult part. And actually, that's not something that we do ourselves, but we outsource this task to other libraries. So there exist libraries, for example, Backpack or ASTL, which implement efficient Hessian computations. And we actually just use these libraries as a backend, essentially, and kind of build our library on top. And it's very easy to also add new variants of Laplace approximations. So if you come up with a new Laplace approximation that you want to try out, it's very easy to implement because it's very modular. And we also provide a default. Like if you look at this flowchart that I showed you in the beginning, you might think, well, how would I know which option I should choose? There's so many options. Which one should I take if I have no idea how these things work? Then we provide actually a default, which works very, very well. So in the paper, we ran a lot of experiments, and we kind of show that there's one particular combination that has a good trade-off between efficiency and performance. And this default is kind of, defaulted in the library. So if you just call it without any arguments, it will default to this configuration. And in particular, this configuration considers the last layer only. So you do only inference over the last layer. So it's a special case of subnetwork inference where you choose the last layer. And for the Hessian, you choose this Kronecker factorization. So you assume kind of block independence between the layers, not between individual weights, but just independence between layers. And there's also a certain predictive distribution, which we found to be best, which is called the probit approximation. Yeah, so this is kind of a very good choice if you want to just try it out. And just maybe one or two more examples. So if you want to use regression, for example, on the top right, you see a simple regression example. And on the left, you see how you can use it. So if you load the model for regression, then you can, for example, put it into this Laplace wrapper in line 5, 6, 7. And here we decided to do inference over all weights and compute a full Hessian, which is actually tractable because the model is quite small. Then we can fit the model and then, optimize the hyperparameters and then make predictions. And then we get, for example, this nice fit with these uncertainties. You can also do classification. If you want to do classification, you can specify other parameters. For example, you can do inference over only the last layer. You can use, again, this layer independence for the Hessian. Then you can fit the model, and then you can optimize the prior precision, for example, also using cross-validation. So there's different ways to optimize this prior precision. One is actually using the marginal likelihood, which is the default, which is also tractable using Laplace. Another option, what people often do in practice, is using cross-validation. For cross-validation, you need a validation loader, right? You need validation data. The advantage for the marginal likelihood optimization, so the default is that you don't need any validation data. You can optimize the hyperparameters using the training data only. But if you want to do cross-validation, you can also do that if you want. And you get quite good performance. So I will not go into detail here, but essentially you can get good performance compared to baselines. And then, one big advantage of the Laplace approximation is that it's actually quite cheap, especially, for example, if you consider the default that we propose of just doing inference over the last layer. It's barely more expensive than map. So on the left, very left, you see the map, so just the normal model. Then one to the right is the last layer Laplace approximation, and you see both the training time in blue and the prediction time in orange are basically the same. It doesn't add any overhead. And this is because you don't have to do, for example, sampling during prediction time. You use the closed form approximation if you use our default. And this closed form approximation gives you uncertainties in a single forward pass, so you don't have to do sampling. Whereas many of the other baselines, for example, here we show variational Bayes, cyclical, stochastic gradient, Hamiltonian Monte Carlo, swag, and deep ensembles. All these methods are much more expensive, both during training and also during prediction, because many of these methods have to do sampling at prediction time, like variational Bayes. It makes them quite slow. And Laplace is very fast here, so it has a very good trade-off between efficiency and performance. And yeah, basically, now to conclude this part of the talk, the take-home message is that, yeah, Laplace approximations have gone out of favor, but due to recent advances, they have been made scalable to modern neural networks. And they're, using our library, they're very easy to use. They're very efficient to run, and they work actually quite competitively across a range of benchmarks. So if you want to see more experiments, check out the paper where we actually show more experiments. And yeah, we did a quick review of modern advances in the Laplace approximation and proposed this library called Laplace. And we hope that researchers and practitioners will use the Laplace approximation again, maybe just as a baseline or even to build upon it and to improve it. But yeah, even if you just want to try it out, feel free to just give it a try and let us know if you find any issues or if you have questions on how to use it. So yeah, with that, I want to thank you for your attention and want to wrap up. And yeah, I'm happy to take any questions. Yeah, thank you so much for your attention. And for
Thank you very much for the presentation. I really like that you guys work on this package, because honestly, I think most people believed in the Laplace approximation. You know, I actually never heard anyone saying that it doesn't work.
Okay.
I've heard several people say that VI doesn't work. I rarely heard people saying that the Laplace doesn't work. I think that some people think that it's intractable, but honestly, everyone that knows about the details know that it can be made tractable without too much burden. But I feel that the biggest reason was that there wasn't a good package for doing it. Like in general, just computing second derivative in PyTorch is clunky. It's very clunky, and just so when your paper involves to do it, you usually don't, because it's not easy to, because there is software work for that. I don't know if you have a different experience of people actually be skeptical of Laplace in itself.
Yeah, I think it depends. So I think some people say it's bad because it's unimodal, right? You only fit like one Gaussian, and the posterior is multimodal. So that's one concern I've heard. And then, yeah, the scalability is, I think, one issue. But as you said, I mean, there has been recent work to scale it, but I think not everyone is familiar with these things. Obviously, like a diagonal approximation, everyone knows about, but I think a diagonal approximation doesn't work too well. So I think some of these other methods that I showed you, like the subnetwork one or Kronecker factorization of the Hessian, works better than the diagonal. So yeah, there's ways to scale it, definitely.
Yeah. No, yeah, I mean, subnetwork sounds very smart, but I mean, everyone knew about Kronecker layer-wise. I mean, it's not particularly sophisticated. I wonder, you didn't mention low-rank approximation, but is it because of performance or for scalability?
Yeah,
because
actually, we weren't aware of low-rank. Yeah.
I would be curious, right? Because then you get the nice things of low-rank that you can add it to whatever you want. So you can get some global weight coupling on the top of whatever other approximation you have. And it's the low-rank update are relatively cheap. So, I mean, everything that is relatively cheap on million of weights is still expensive. But eventually they're dot products.
No, that's a very good point. Actually, when we submitted the paper to NeurIPS, we didn't have anything on low-rank in the paper. And then one reviewer pointed out that there has been work on low-rank approximations for Laplace. And they pointed us to some papers, and then we actually implemented it. And for the rebuttal, we presented also results with low-rank. And it seems to work quite well. So in the next release, so it's not supported right now, but in the next release of the library, we will also support low-rank approximation to the Hessian, and it seems to be quite competitive. So yeah, that would be also cool to try more extensively. So that's a very good point.
I mean, you have the low-rank update formula, right? So you can use the low-rank for improving everything you want with a decently small overhead. So you can take your subnetworks and get a couple of low-rank updates for getting some globality there.
Yeah, exactly. I think that's a very promising avenue. I agree.
Yeah, that's exciting. Yeah, hopefully we're going to see much more of this in the future, because I think, yeah, as you said, it's been unfairly neglected. What do you think about about the multimodality? As you said, I mean, I think it's partially a red herring, because most people who are in the field think that well, first of all, multimodality is not always useful, right? Multimodality is often a sign of symmetries, and often you want to, often the other modes are equivalent, so you don't necessarily want to capture them.
Yeah.
And that's, you know, networks have huge symmetries, so most of those modes are equivalent.
Yeah.
And it's, I think most people who have experience in Monte Carlo think that properly capturing the multimodality is quite hopeless. So I feel a lot of people say multimodality, yes, but people who are actually into the field think, yeah, you're not going to get it. Just focus on getting your mod right.
I totally agree. It's very challenging to get. And as you said, due to symmetries, you might often get the same predictions with the different models. But yeah, still, I think there's papers showing that deep ensembles are very good. And actually, the most recent work that I've been involved with tried actually to combine the benefits of deep ensembles. So try to combine the multimodality with the Laplace approximation. So we have a paper actually at the Bayesian deep learning workshop at NeurIPS, where we simply kind of do an ensemble of Laplace approximations. So it's a very simple idea, right? You just train multiple models independently, you do Laplace approximation over each of them. And we show that this at least can improve upon deep ensembles, and it also improves upon Laplace. So I think there's some benefits to multimodality, but as you said, it's very difficult to actually get very diverse, explore very diverse modes, right, in the posterior. So I think until this challenge is not resolved, yeah, there might not be too, benefits might be, yeah, not too obvious, because obviously you have also more expense, right? If you have an ensemble, you have 5 models that you have to keep around, so it makes it much more expensive. So it's not clear if the benefit is big enough.
But also, is the benefit due to multimodality? Because again, it's unclear whether the network will converge to different modes, because it could be that, I mean, they almost certainly would converge to superficially different mode, but it could be that they're all linked by the same symmetry. And it could be that the advantage is posterior coverage of the mode, not necessarily multimodality. And that's difficult to see in high dimension. I'm sure in low dimension you can prove that you get advantage from multimodality, and you know we can do multimodality in low dimension, right?
Yeah.
But I think it needs to be proven that those modes are different substantially.
Yeah.
And I mean, I didn't follow the literature that closely, so it could be that actually there are good evidence. But I wouldn't be surprised if there's somebody just covering that mode well.
No, that's a super good point. I totally agree. There needs to be more research. And I also think at high dimensions, it's very difficult to actually see if models are different or not. So yeah, I think there's a lot of potential for future research in this direction. Yeah. Yeah, thanks so much for your comments, Luca.
You're welcome.
I appreciate it.
I'm sorry for missing the beginning of your talk.
Oh, no worries. I think there's going to be a recording, so
Yeah.
if you're interested, you can rewatch. But then, yeah, thanks so much for your attention and for the great discussions. And yeah, John, really just thanks so much for the invitation. It was very
thank you for presenting. It was very
great to talk to you. And yeah, hope to see you soon at some conference maybe, or
yeah, hopefully at the Bayesian deep learning workshop, because we're going to present something as well. So